Welcome to Ask and Learn.
For this problem, we'll use the integral test. For the integral test, we want for these terms to eventually be strictly decreasing in absolute value to 0. So for that to happen, you would want for this to eventually just be increasing. So typically speaking, if you know that these things are going to be going to 0, then you can guess that they're going to be going to 0 in absolute value, unless you have some trig functions involved, because with trig functions, you can imagine there being some oscillations occurring. But generally speaking, it's a fairly good guess. If it looks like it's going to 0, then it's probably going to be going to 0 when you throw the absolute value signs around it as well. Like I said, the exception typically being with trig functions. You have to be a little bit more careful with that. But it is true, if you want to be really rigorous, then you should look at this. You could take the derivative of this and show that eventually the derivative is going to be positive. If the derivative of this is positive for n large enough, then that means that eventually this is just going to be decreasing to 0. Okay, so the integral test is applicable here. So the integral test says that this thing is going to have the same behavior as this integral. Okay, so this is a u substitution problem. So the u would be ln of n. du would be 1 over n dn. So then the integral in consideration turns into ln of 2 infinity u to the minus 1/2 du. So this lower bound here, we got that from looking at the lower bound over here. So over here, our lower bound was 2, and that corresponded to n. So when n is 2, plug in n as 2 here, and we get that u is natural log of 2. So that's why when we're working with du, our lower bound is natural log of 2. To get the upper bound here, we look to see what's happening with the upper bound here. So here, this corresponds to n being infinity. So when n is infinity, u is natural log of infinity, which is still infinity. And then we replaced the 1 over n dn with du. That's what this equation tells us we can do. And then we were left with du 1 over square root of natural log of n. But natural log of n is just u. So we're left with 1 over the square root of u, which is just u to the minus 1/2. Okay, so of course it would be, if you're working with du, you want everything to be written in terms of u. So that's what these equations tell us to do. We know what to do with the dn. We know what to do with the natural log of n. We can use these equations to express everything in terms of u, and we can change the bounds by looking at the bounds up here and figuring out what the bounds correspond to by this top equation. Okay, and then once we have this guy, this is just, we can just use the power rule. And we get 1/2 u to the 1/2. And then we're evaluating this from natural log of 2 to infinity. And this is certainly going to be something that is infinite, right? If we plug in infinity here, we're going to get something that blows up. And then we're subtracting what happens when we plug in natural log of 2 in for u. So we'll have infinity minus something finite, certainly going to be infinite. Okay, so since this integral turns out to be infinite, the integral test tells us that this sum is also going to be infinite, which means that we get divergence.